Welcome, myself Gksr from Department of Electronics and Communication Engineering. Today I'm going to explain the subject digital communication, having subject code of 18EC61. The topic for today's presentation is properties of Fourier properties. It was presented by me, Gksr. Moving to the next slide. Uh, First, we need to understand what are the different types of Fourier transform. The different types of Fourier transforms are given here in the slide, that time shifting property, scaling property, linearity property, frequency shift property, differentiation property, integration property, convolution property. These are the some of the different types of properties of Fourier transform. In detail, we will study in the next slides. Uh, Moving on to the next slide. Time shifting property. The statement for time shifting property is the time shifting property of Fourier transform states that if a signal x of t is shifted by t naught in the time domain, then the frequency spectrum is modified by a linear phase shift or slope of minus omega into t naught. In detail, we will explain in the below derivation that mm, if f of x of t Fourier transform is x of w, then x of t minus t naught is e power minus j omega t naught into x of w. The proof for this time shifting property is given here in the slide. A Fourier transform of x of t minus t naught is equal to integration minus infinity to infinity x of t minus t naught into e power minus j omega t uh, dt. Uh, Let x of t is equal to z, which implies t equal to t naught plus z. Also, as t changes to infinity, capital T changes to infinity too, at as t naught as at t is changes to infinity, capital small t is also changes to infinity. Fourier transform of x of t minus t naught is equal to integration minus infinity to infinity x of t e power minus j omega into t minus z uh, into dt. Which is equal to e power minus j omega t naught into minus integration minus infinity to infinity x of t e power minus j omega t dt. Fourier transform of x of t minus t naught is equal to e power minus j omega t naught into x of omega. Hence, we can prove the time shifting property from this derivation given in the slide. Moving on to the next property, linearity property. The statement states that the addition of two functions corresponding to the addition of two frequency spectrum is called linearity. The addition of two functions corresponding to the addition of two frequency spectrum is called as linearity. In detail, we will see that if x1 of t for a transform is x1 of omega, and x2 of t for a transform is x of omega, then a into x1 of t plus b into x2 of t for a transform is ax2 of omega plus bx2 of omega. In detail, we will see the proof f Fourier transform of ax1 of t plus bx2 of t is equal to integration minus infinity to infinity ax1 of t plus bx2 of t for minus j omega t dt. Mm, Integration minus infinity to infinity ax1 of t. To we can we can see the derivation from here. Hence, we can say that hence we can prove that the linearity property of the the linear. Hence, we can prove that the linear property. Moving on to the next property, frequency shift property. The statement states that the frequency is shifted according to the coordinates There is a duality between the time and frequency domains, and frequency shift affects the time shift. And it can be explained clearly that if x of t Fourier transform is x of omega, then x of t in t power j omega t is equal to x of omega minus omega naught. It can be proved. It can be proved in the given way at PPT level. We can see that Fourier transform of x of t into e power j omega naught t is equal to minus infinity to infinity x of t into e power j omega naught t into e power minus j omega t, as Fourier transform is allows minus, which implies integration minus infinity to infinity x of t into e power minus j. We need to take common e power minus j t into the remaining terms of omega naught minus omega naught and omega. Um, Hence, we can prove the frequency shift property. Moving on to the next slide, scaling property. Scaling is a method that is used to change the range of independent variables and features of data. If x of t Fourier transform is x of omega, then x of at Fourier transform is 1 by modulus of a into x of omega by a. The proof is clearly given in the PPT. Um, we can see the proof of the scaling property from the proof given in the PPT. We can verify the scaling property, uh, and then moving to the next slide, differentiation property. The statement states that the differentiation function with respect to time yields to the constant multiple of the initial function is known as differentiation property. It can be stated that if x of t for a transform is x of omega, then differentiation of x of t with respect to time will gives j omega into x of omega. If the differentiation, if we differentiate again in the sense d square double integration of x of t with respect to time gives j omega whole square into x of omega. If there is d cube, in the sense triple integration of x of t with respect to time will gives us j omega whole cube into x of omega. This is known as differentiation property. The proof is given in the slide. From the proof we can from the proof given in the slide, we can clearly verify the differentiation property. Moving on to the next slide, integration property. The time integration property of continuous time Fourier transform states that the integration of function x of t in time domain is equivalent to the division of its Fourier transform by the factor j omega in frequency domain. In simple manner, if x of t Fourier transform is x of omega, then integration from minus infinity to some time interval t x of t dt is Fourier transform is x of omega by d omega. Um, the proof can be given in the slide. You can uh, verify the slide for the proof of integration property. Uh, and then next property is convolution property. Convolution property, it includes the multiplication of two functions. The Fourier transform of convolution of two functions is the pointwise product of their respective Fourier transforms. In a simple manner, x1 of t is Fourier transform is x1 of omega, and x2 of t Fourier transform is x2 of omega. Then x1 of t convolution with x2 of t implies x1 of t into x1 of omega. Um, the proof can be shown in the PPT. It can be used to verify the convolution property. Hope you understood the concept. I feel so grateful for presenting in front of you. Myself Kedar Sarangya, and then thank you for listening to the class. And then bye bye.